Chapter second. Neurohormonal transmission. Chapter second. Neurohormonal transmission. Neurohumoral transmission. Neurohumoral transmission. Neurohumoral transmission implies that nerve transmit their message across synapses and neuroeffector junction by the release of humoral chemical messenger. Historical aspect. 1857. Du Bois Raymond observed similarity between transmission of nerve impulse produced electrically as well as by chemical substance such as ammonia, lactic acid, etc. 1901. Lewandowski and Legally noted independently the similarity between the effects of injection of extract of the adrenal gland and stimulation of sympathetic nerve. 1910, Berger and Dele noted that the effect of sympathetic nerve stimulation were more closely produced by primary sympathomimetic amines than by secondary sympathomimetic amine. 1914, Sir Henry Dele thoroughly investigated the pharmacological properties of acetylcholine, which produce response exactly similar to parasympathetic nerve stimulation, and he introduced the term parasympathomimetics to characterize the effect of acetylcholine. 1921, Otto Levy provided the first direct evidence for the chemical mediation of nerve impulses by peripheral release of specific chemical agent. He electrically stimulated the vagus nerve of an isolated perfused frog heart. The perfusate leaving the preparation was reperfused through another frog heart. Upon stimulation of the vagus nerve to the first heart, Levy observed that this heart was immediately depressed. Within a few seconds, the second heart was also depressed. Certainly, the most logically explanation of this find was that stimulation of vagus nerve liberated a chemical myocardial inhibitory substance that was carried in the perfusate to the second heart. They referred this substance as vagus substance or parasympathine, which was later recognized as acetylcholine. 1946. Von Euler, he showed that the sympathetic transmission is noradrenaline criteria of being a neurohumoral transmission. Criteria for being a neurohumoral transmission. To be considered as a post-junctionally acting neurohumoral transmission, a substance must fulfill the following criteria. It should be present in the presynaptic neuron, usually along with the enzyme synthesized it. It should be released in the medium following nerve stimulation. Its application should produce response identical to those produced by nerve stimulation. Its effect should be antagonized or potentiated by other substances which similarly alter effect of nerve stimulation. Step involved in neurohumoral transmission. Axonal condition and axonal conduction. Axonal conduction refers to the passage of an impulse along a nerve fiber. It is dependent upon selective changes in the permeability of the axonal membrane to electrolytes. At rest, membrane potential within mammalian axon is approximately -70 mV. This negative intracellular potential is maintained at rest basically because The axonal membrane is more permeable to K plus than to Na plus. Na plus ion are in highly concentration in extracellular than in intracellular fluid, whereas K plus ion are in greater concentration in intracellular than in extracellular fluid. The relatively small amount of K plus that leak in the interstitial space in conjunction with the large number of organic anions that are intracellular result in a net negative charge within the axon. An axon potential reflects a reversal of the polarization state present at rest and is the result of permeability change that occurs at the axonal surface as an impulse is propagated along a nerve fiber. A suprathreshold stimulus initiated a localized change in the permeability of axonal membrane. Suddenly, permeability of the fiber to Na plus ion is greatly increased in relation to K plus. Na plus move inward in the direction of its large electrochemical gradient. The movement is detected by an instantaneous change in the membrane potential in a positive direction. The positively charged Na plus increase in concentration within the axon. The membrane potential move from minus 70 millivolt towards 0 and then overshoot to the extent that momentarily the inside of the fiber is positive in relation to the exterior of the cell. Repolarization of the membrane occurs rapidly as the selective permeability characteristics of the axonal membrane are quickly re-established. The axon once again becomes relatively impermeable to Na plus and relatively more permeable to K plus, and the negativity of the interior of the cell is quickly re-established. Although not important in axonal conduction, K plus, calcium plus ion in other tissue, example heart, contribute to the action potential by prolonging depolarization by an inward movement of calcium plus ion. This influence of calcium plus also serve as a stimulus to initiate intracellular events. Although the localized permeability change associated with an action potential are extremely short-lived, they elicit similar alteration in membrane function in immediately adjacent quiescent area of the axon. Thus, the axon potential is a self-propagating, and in this manner an action potential is conducted along an axonal fiber. Axonal conduction is insensitive to most drugs. Even local anesthetic must be used in high concentration in immediate contact with a nerve before excitability is blocked. The axonal conduction is blocked by certain toxins such as tetrodotoxin, pufferfish poison, and saxitoxin, shellfish toxin, which interfere with the Na plus entry across the neuronal membrane during depolarization. Batrachotoxin, a steroidal alkaloid toxin elaborated by a type of South American frog, paralyzes the nerve by persistent depolarization as a result of increases in Na plus influx. Local anesthetics act by preventing the Na plus influx and depolarization of the nerve. Junction transmission. Junctional transmission. The arrival of the action potential at the axonal terminal initiates a series of events that trigger transmission of an excitatory or inhibitory impulse across the synapse or neuroeffector junction. These events are as follows: storage and release of the transmission. Storage and release of the transmission. The non-peptide neurotransmitters are largely synthesized in the region of axonal terminal and stored there in synaptic vesicle. peptide neurotransmitters are found in large dense coarse vesicles, which are transported down the axon from their site of synthesis in the cell body. During the resting state, there is a continual slow release of isolated quanta of the transmission. This produces electrical response at the post-junctional membrane miniature and plate potential maps that are associated with the maintenance of physiological responsiveness of the effector organ. A low level of spontaneous activity within the motor unit of skeletal muscle is particularly important since skeletal muscle lacks inherent tone. Release of neurotransmitter substance is triggered by arrival of the axonal action potential at the nerve terminal. The action potential causes the synchronous release of several hundred quanta of neurotransmitter. Depolarization of the axonal terminal triggers this process, a critical step in most but not all nerve ending in the influx of calcium plus, which enter the axonal cytoplasm and promote fusion between the exoplasmic membrane and those vesicles in close proximity to it. The content of the vesicle include enzyme and other proteins then are discharged to the exterior by process termed exocytosis. Combination of the transmission with post-junctional receptor and production of the post-junctional potential. The combination of the transmitter with post-junctional receptor and production of the post-junctional potential. The released transmitter combined with the specific receptor on the post-junctional membrane and depending upon its nature and excitatory postsynaptic potential EPSP or an immediate postsynaptic potential IPSP is produced. EPSP excitatory postsynaptic potential. Increase in permeability to all cation causes Na plus or calcium plus influx through fast or slow channel, which cause depolarization followed by K plus efflux repolarization. These ionic movements are passive as the flow is down the concentration gradient. Electrically, these changes are characterized as excitatory postsynaptic potential, which then propagates localized permeability changes in adjacent portion of the cell membrane, and an action potential is conducted along the remainder of the inverted cell. IPSP. Increase in permeability to similar ion, example K plus and calcium A plus chloride hydrated K plus ion is smaller than hydrated Na plus ion, only so that K plus move out and chlorine move in the direction of their concentration gradient. Thus it causes an increase in the net negative charge within the cell and actually hyperpolarize the postsynaptic membrane. The resulting hyperpolarization of the membrane increase the threshold to stimuli and in effect elicit an inhibitory response in the cell. Initiation of post-junctional activity. Initiation of post-junctional activity. If an EPSP exceeds a certain threshold value, it initiates a propagate action potential in the postsynaptic neuron or a muscle action potential in skeletal or cardiac muscle. In smooth muscle, an EPSP may increase the rate of spontaneous depolarization, affect the release of calcium plus, and enhance muscle tone. In gland cells, the EPSP initiates secretion through calcium plus mobilization, and IPSP, which is found in neuron and smooth muscle but not in skeletal muscle, will tend to oppose excitatory potential simultaneously initiated by other neuronal sources, destruction or dissipation of the transmitter. Destruction or dissipation of the transmitter. Following its combination with the receptor, the transmitter is either locally degraded acetylcholine or is taken back into the prejunctional neuron by active uptake or diffuse away any GABA. Rate of termination of transmitter action governs the rate at which response can be transmitted across a junction 1 to 1000 per second. Thank you.